but yes, everything is recorded, so we should be fine. Anyway, so for today's lectures and for these two topics, we will be going over, kind of like go back to the clustering algorithms again. And the algorithm that we would look at today would be the following two algorithms. The first one is the Gaussian mixture model, or GMM, but this will be on lecture number 17. Anyway, for the current lecture is actually DBSCAN. But the reason that I would like to talk about DBSCAN first is because it's actually, doesn't have a lot of, how should I say, it's like at the moment for DBSCAN, what we will look at would be like more like algorithm side of it. We wouldn't go over the technical detail as in, like the optimization problems and stuff. But it's more because DBSCAN is the arguably very famous algorithm right at this moment. And actually, it has a lot of benefit over the K-mean, and actually more efficient than GMM, and that's the reason why it becomes like one of the first choices when people want to try on some clustering algorithm. Okay, so before we go over to what they are, let's go back a little bit about the K-mean algorithm. We know the K-mean algorithm is like the algorithm that starts off with that you have set of data, you don't know what cluster they are, but you kind of know the number of cluster beforehand, and you give that as like a hyperparameters to other algorithm. After that, the algorithm will then start to, like randomly initialize each data point to one of the clusters. After that, you will then compute the centroid of these randomized cluster samples. Then, whatever points that are close to the centroid will be identified as that class. For example, any point that is close to this yellow will then be identified as yellow cluster. Whatever points that is close to this pink point will be identified as a pink cluster, and whatever points that is close to the green point here will be identified as a green cluster. So after you identify that, you then recompute the centroid again, and the centroid of the cluster will start to shift to the middle area of each cluster, and you will keep doing this, like reassigning and then compute the centroid and then reassigning the cluster, so on and so forth, until you get the centroids that are consistent. That is, the centroid of the cluster will no longer change, and then you stop, and that's where the K-mean algorithm will say converge, and that is what K-mean is. So there are a few things to notice about. For example, firstly, when you kind of put the samples into cluster and say that it's, it's based on the closest centroid to that point. Let's say if you are looking at this point and the closest is this one, it's kind of like, how should I say? It's like the way that the clustering is performed would look as if you are drawing like an equal radius circle over an area. And that is because the only thing that you shift is the centroid, and essentially whatever closest to that centroid is kind of like it's try to optimize for the shortest distance to that centroid. And that's the reason why the resulting clustering would look as if it was like a blob of points, or what people might call like an equivalent radius, like a circular area shape, which if you compare that to the algorithm that we would learn today, that is, let's say, the GMM, if you have the data points that kind of look like this, right? K-mean will choose whatever that is close to the centroid, and you probably can guess that the centroid of K-mean would be around here, another one is here. Whatever is closest, it's gonna be something like it, as if you kind of draw a circle there and another circle there. But the thing is, it doesn't really shift the clustering towards the data distribution. And that's because K-mean was using just Euclidean distance. There's no density awareness inside it. It just said whatever closest to the centroid, that is going to be the points belong to that cluster. Meanwhile, Gaussian mixture model and the DBSCAN, another algorithm that we will learn today, will have some kind of features that we call density awareness. In GMM, the algorithm will be able to estimate the variance of the cluster and re-identify that cluster. Therefore, if you have the data distribution that, kind of like you can tell that this is definitely like a mix of data samples that, definitely is not just a single variance, it's probably two variants around there. GMM would be able to identify that. But, and yes, DBSCAN as well will be able to identify a cluster that is kind of like this, not exactly the same, but somewhat in a similar sense that it can differentiate this cluster away from this cluster. And that's kind of the key here. But K-mean wouldn't be able to do anything like that because everything is based on the distance. Another thing about K-mean is that it cannot tell whether or not the point that is included into the cluster, let's say this one, is essentially a data point or noise. This is another weakness of the K-mean algorithm. So, if we talk about K-mean, we can tell that, okay, K-mean will be the algorithm that make a hard decision. Hard decision means that you just simply said it belongs to this cluster over that cluster, kind of like you assign a value to that sample point. So that's like an integer cluster number to that. So that is what we call hard decision. Another thing that is, it's kind of judge everything based on the Euclidean distance, and therefore it's often result in a cluster that look like a circular shape. Meanwhile, when we talk about the density awareness, it's actually lack the judgment for data density because everything based on what is the closest. Yeah, so that's kind of the weak point of K-mean. Also, in terms of hyperparameters, it requires to know the number of clusters beforehand. So you have to kind of guess before you use it. And lastly, it cannot identify noises, like it takes every data point as data, even though that may be like a noise, it doesn't care. And yes, if you have the noises that cluster together, chances are you're gonna have that as a new cluster as your result. So this is the problem with K-mean. And what about these two algorithms that we would learn today? Actually, these two algorithms will have special features or maybe special assets to address those issues in K-mean. For example, let's look at the DBSCAN, the algorithm that we will look at today. DBSCAN will be very similar to K-mean in the sense that it will also make a hard decision to which the cluster that samples belong to. But the good thing about DBSCAN is that it can perform clustering based on data density. But you will see the difference between DBSCAN and GMM, as in GMM will make a rather, like it uses density as a driven mechanism, but the way that it performs clustering for GMM will be based on probabilistic model. So the result of clustering from GMM will be like a soft decision, and it's like a soft decision based on density estimation. But DBSCAN will be purely like empirically the density that you kind of like draw a hard area and say what is the density in this area. So that is DBSCAN. So in here, I kind of give it a plus sign. That means it's different, or maybe like a feature or attributes that is not, it's something that wasn't existed in k-mean, but existed in DBSCAN. But 0 would just mean it's the same. Yeah. Another thing about DBSCAN is that it can handle noise. In fact, it can separate the noise. That's actually very important, can separate the noise. Or can identify. Okay, I will just say identify. It can identify the noise. And that's actually something major for this algorithm, because most of the time when we have, data samples that are input features and we don't have labels, it's very hard to tell whether or not that data samples are actually the data or it's actually some kind of interference in your system. So some people might use DBSCAN to do some cleaning. That is to identify whatever outliers that doesn't seem to belong to, it seems like it's like aliens outliers. So some people would use DBSCAN to remove that outliers first. And after that, they would use the rest of the data to perform something else, but that's sometimes, most of the time, what people would do if they don't have other choices. And another good thing about DBSCAN is that it does not require the number of clusters to know beforehand. And that's kind of reason why when people want to do some clustering, they will start off with DBSCAN. Because first, you don't need to predefine, like the important parameters, that is the number of clusters. You can just allow the data to drive your clustering algorithm to provide the result. And also it can identify noises. And actually lastly, even though here I said that it requires more computational cost than k-mean, but actually the computational cost is actually quite scalable to big data. So that means that you can still use it even though you have a lot of data points. It may not be as fast as k-mean, but if you think about what k-mean does, is the procedure of k-mean is very minimal. It's just computing the Euclidean distances with the centroid, which is very, very much like only few operations. But if you think about the benefit that you would get out of DBSCAN, that was a lot better. Like what's the noise, and the number of clusters beforehand. And yes, that's the kind of reason why people might use DBSCAN before anything else, because it can identify the noise and it can tell you roughly what could be the number of clusters in your data. However, the performance of DBSCAN also depends on two parameters, which we will talk about today. That is, the first thing is like a radius value. And this radius will identify like a size of neighborhood to a point that you're considering. Another thing is the number of neighbors points within the clusters, within the radius, including the central point itself. So that's the two parameters. We will see how it works, but that just let you know that's the two parameters that's given. Okay, compare that DBSCAN to Gaussian mixtures model, even though we haven't learned it yet, but I'll just give you a rough idea, kind of like why people would talk about these two together sometimes. The reason being is that when you learn about GMM, you may find that actually Gaussian mixture model, even though fundamentally it's so different from k-mean, but actually I would say the procedure of Gaussian mixtures model clustering is very similar to k-mean. But the difference between the two is the fact that Gaussian mixture model will provide the clustering based on density estimation, and the result will be solved decision. So you can see that there's only 2 plus when you compare it to the DBSCAN that is like 3 plus. And the other two of GMM, that is, it cannot handle noise. I will put it this way, it's not exactly that it cannot handle noise, it's more like it cannot identify. It's robust, more robust to noise. then k-mean and the hierarchy clustering, but it cannot identify the noise. It's just more robust, and we will see why. Actually, you can use some thresholding trick to tell whether or not that data points are noises, but it's just like you need additional procedures to do that. Meanwhile, DBSCAN will be able to do that right away, that it can just tell right away that these samples are noise. Given these two parameters, it must be noise, something like that. And another thing about Gaussian mixture model that is not so far away from k-mean is the fact that it does need the number of clusters. So I'll put it this way, if you start off with trying to, perform some maybe data pre-processing, where you have data samples that only contain input features, you don't have the label, and maybe you want to use clustering algorithm to do the labeling, let's say, but you just don't have label, but you aim to use this clustering algorithm to give that label. What people would do, they would normally start off with DBSCAN to tell you roughly how many clusters, or kind of like could be translated to how many classes that's going to happen roughly, and what are the noises. With DBSCAN, you can tell that first. After you have DBSCAN, you would know roughly what could be, like the size of the radius that you should consider for the cluster to be. After that, you may start using either the k-mean or the GMM, but people, if they want something more precise, they will use Gaussian mixture model to provide like a soft score, and also, because it can handle noise better, more robust, I would say. It's more robust to compare to the k-mean. So it, when it interfered by noise, it wouldn't give you like a drastically wrong result. It gives you roughly what the result could be, but that result would come with some kind of soft score. And that soft score or soft decision would tell you roughly whether or not this samples is noise, or it's just, just a variance of your data. Because you can imagine that, if you do clustering, you would probably see this a lot. Let's say, it's not clustering, classification. Sometimes when you take pictures of an object, and sometimes maybe you take it from a very weird camera angle, it's still the same object, but it's just that the appearance, or maybe the input features that you get from that image would be a lot different from others. But it can still somehow be clustered or be classified as that class. Versus if you take like a sample that's purely noise, that sample probably contains something that is not something that you're considering. So that's noise, right? Yes, so I'll put this way, DBSCAN is usually being used roughly identify, and then Gaussian mixture model would be something that more precise, something that is, give you more insight as well into what is going on, because the result of Gaussian mixture model will be like the score that you can further interpret. Actually, it's actually a very good algorithm to start with if you want to further analyze your data. Like if you want to analyze something, maybe try DBSCAN, check whether it's noise, check how many samples are there, what are the clusters, and then do the GMM. The GMM would give you a lot of insights. Yeah, but yes, probably the question would be then why we have to learn k-mean and hierarchical. The answer would be if your data is clean, hierarchical could give you a better insight to how your data are related. But the k-mean algorithm would be like the fastest option, the simplest. Maybe it's good to give you intuition of what's going on with this clustering algorithm. And actually, mathematically, it's the very direct way to derive from, that optimization problem that we've seen before about how clustering works. Yeah. Okay. Now we will go over DBSCAN, and please don't worry, DBSCAN contains only 1 slide, 2 slides, 3 slides, and that's it. And then we'll take a break. It will be very quick. All right. So DBSCAN. Okay, people would not called the full name of DBSCAN because here's this full name: density-based spatial clustering of application with noise. It simply means it's the clustering algorithm that can be used with noise, and it's density-based. But in short, we call it DBSCAN. Actually, DBSCAN has like a, another version of it. I'll put it this way: it's like a more updated version of DBSCAN. It's called DBSCAN. And I'm not sure, but you can check further. I kind of remember the H is from like hierarchical. Like it's like a DBSCAN version, but then they do some hierarchy inside it. And anyway, today we will just look at the density-based, the DBSCAN. The way that DBSCAN works is driven by the way that it classify, or maybe it kind of like putting data points into 3 types of the points. So there are the core point, border point, and noise point. And as we probably can guess, noise point is definitely the noise. I mean, the data samples that DBSCAN will identify as noise. But the points that will actually form the cluster will be the core points and the border points. And actually between these two, core points is the one that is used to initialize the cluster and identify the neighborhoods of that cluster as part of the clusters. Meanwhile, border points will be points that kind of important, but it's not really satisfy all the criteria for being the core points. And that's why we have the border points, but we will show you this example. So there are 2 parameters, as I mentioned before. One is the radius E, or mu. Some people would use some signs for it. And another parameter is the number of neighbors. Actually, it's like the number of points within the circle of radius E. So let's say we are considering these points. And we say that the radius E is about this. And then you have k equal to 3. In here, k will be the number that say what is the minimum points within this area that will consider that these points are important, such that the core, the one in the middle, will be identified as core. So on the other words, if you check all these 4 points, let's say you start off with this yellow one. If you draw a radius and count how many points are there, it's just 1 and maybe 2. It's not 3 yet. That means this one is just a border. And, border. Meanwhile, this one, if you move to this point, you draw a radius E, and then you count how many points are there. There are 3. So therefore, this one will be a core point. Then you move to this one. Then you do it again. That is, you move to this one and you draw a radius E and count how many points are there. There are 3, therefore this must be like another core point. And then lastly, for this yellow, you draw E, there are only 2, therefore this is not core point. It's a border point because it's actually part of other core, but it's not the core point itself. So it's border. And what about this one? This one, if you draw a radius E, you found no one. It doesn't be parts of anything or belong to anyone or even not a core point itself. Therefore, we call this kind of points the noise point. So in this algorithm, it kind of identify cluster in this manner. That is, it first started with identify the core point, then find the border points. It's kind of like when you find core point, you will automatically check whether or not that was border or core. Yeah. But then at the same time, you find the noise. But the actual mechanism that formed the clustering is when you find a core point, let's say if you say that these, I will use a better example. Let's say if you have this point, this point, this point, being core point, and let's say if you say that, okay, the core point will be the point that contain at least 3 neighbors, and let's say these are definitely identified that that one is core. Okay. And if you look at another one, this one, yeah, it still be a core. This kind of like 4, maybe, yeah. Okay, maybe I'll shift this out a little bit because it's actually violating. Maybe this one is kind of here. And when I look at this one, maybe this one still being a core point. Then, you know, when you circle, but maybe this one is not. Let's say this one is not, this one is core point, and it's kind of connect to the other green, let's say. Let's say this one is not, because when you draw a circle, it's just not. The way that the algorithm works would start off with, when the algorithm know which points are core points, when they know that, you know, these red dots are core, it will randomly pick the core points. Let's say if it's randomly picking this point as a core point, then it will start looking at those points that is overlapping with these neighbors. That is, it will kind of do something like growing the neighbors. For example, if it started off with this, it may start finding the neighbors. It knows that, okay, this core point is included. Then it look at the core neighbors of this one. Then it starts circling. Okay, we know that this one kind of in the same cluster. And we look at this one. Perhaps when this one kind of like, you know, they have these 2, but these 2 are border, and there's no other core point within this area, the clustering will stop identify the first cluster just like this. So what happened is that after it identify all the overlapping neighbors like that, these core point will be the core point of the first cluster. And then it will start randomize again, and maybe it will find this one. But this one, I mean, as it's a core point, it will not go back to reconsider any other point that have already been identified. So it will start progressing from, let's say, this direction and maybe onward to others. So the border points has like a function of kind of like, you know, provide some kind of boundary between cluster. And it kind of help the algorithm to not go over the same location again and again. But yeah, it is like, sometimes this situation would happen where you have 2 clusters really close to one another. This is how DBSCAN can separate them, because they have the border points. Yeah. Okay, so let's go over this another simple example. Let's say we have these data points, and let's say it's randomized this pink color as a randomized core point. Then what it will do, just like previously, it start growing, like whatever overlapping with this are core point of that, and then it start to grow. And eventually it would grow to something that look like this, or the pink thing. And then when all these clusters are identified, it belongs to, like, let's say the first cluster, it will just count the number of clusters automatically. And then it will start searching for the next core point, and then it will randomize one, which it could be either one of these group, right? Let's say if it's this one, then it will start to grow the neighbor of that one, and to the point that it can identify all the overlapping point. And if it's finished, like it sort all of that, then that become like the cluster number 2. And for the rest, because there are only 3 clusters, the next randomized will be somewhere in here, right? And then it will start to, you know, growing the point. and they will all be like a core point of the third cluster. Thing is, whatever points that was like a border points, if it's connected to that cluster, it will be shifted toward that cluster. But if you have situation like this, like where you have a border points that is kind of, at the middle between the two, it depends on how the algorithm is written. It could either be that this point would belong to this red one or a pink one, but anyway, if you have data point like this, it actually doesn't matter because it can be either anyway. Right, so that's how the algorithm works. For any point that is really far away from others, they are going to be the noise. Like you can identify the noise, it's kind of, look like the outliers, it not really go with anyone. But if you think about this, the noise are the points that does not fit in to that radius that we set up. And actually, if you think about this radius and the number of points inside, this is density. So let's say if there are more points within this area, that means this area has high density. So that's why we call it density based. That is because the way that we classify whether or not this is a core point or border points is based on the density, whether or not it's dense enough. And that density is, kind of like the number of points that we predefine, that if you have this minimum number of points and higher than that, then that area should be data, and whatever points that have that feature, they are core points. So in this algorithm, the density will be defined by first this radius, right? The larger the radius, the more likely you're going to include your neighbors in. But if your radius is too small, the chances are you're going to get that every point can be, okay, it depends on k. If you say that you only need one another neighbor, that means any point could be cluster itself. So yes, the performance of DBSCAN, especially the density counting, depends on this epsilon and k. So if you have a very small epsilon and the k is very high, which is very, very unlikely, if you define something like that, that means you are assuming that your data samples are the one that is tightly clustered together. But if you relax this epsilon to something really big, chances are you're going to include noise as part of your clustering. So yes, it depends on how you define these two parameters. And because they are parameters, hyperparameters, you can actually tune for the number using validation. So you have validation set to find what is going to be the best for this epsilon and k. Yeah. So that is all for this algorithm, and this is just a result. Like I have run this code and I get this result. Anyway, you can implement it yourself as well. Just look at, I have embedded this link, XBeat here. You just click here. And it will show you the page where people actually provide the implementation of this DBSCAN algorithm. And by implementation, I mean exactly how DBSCAN, identified call points, neighbor points, and everything. You can just look at this implementation and, debug each step. So you will see how they actually grow the neighbor points, how did they actually grow, the cluster area. That will be, you can see it from here. Yeah. And I have run the code, it actually works, but whatever they provide here is actually like a README file. You have to copy this entire page, put it in, let's say, Jupyter Notebook. It will be able to run, I think. Yeah, you can try. Yes, so nearly there. Actually, before we go to a break, this is something that I would like for you to keep in mind. My final exam may not be this exactly, but it would ask you questions something like this. Like, can you tell the features, the properties inside it? Let's say, which algorithm need number of cluster? You should be able to tell it's k-mean and Gaussian mixture model, something like that. Yeah, and yes, is it noise aware? Like k-mean is not noise aware, hierarchical not noise aware, GMM is not noise aware, DBSCAN is noise aware. But which one is robust to noise? You can probably say it's DBSCAN and Gaussian mixture model. Yep, so robust to noise is these two. But we will see why Gaussian mixture model would be like an algorithm that is robust. Yeah. And can you tell what are the hyperparameters associated with each of these? You know, because hyperparameters is another factor that could be like, if you want to use it, you probably want to start with the one that require the least assumption about your data, right? Because you want it to be data driven and you don't want to put a lot of work on that. So yes, this is something that probably be asked in the exam. Anyway, let's take a break and we'll go to another topic.